The SilverHat booster can be built and configured in several versions, either for just DCC or combined with Loconet, and it can provide track current for up to 6 layout districts with up to 8.5 amps track current each. In video number 143 I showed how to build and configure a very simple version, a DCC booster with just 2 output channels. In this video I am going to show how to upgrade it to the Plus version for DCC or Loconet, along with the additional features and configuration options. Hello everyone and welcome to the IoTT channel. I am Hans Tanner. A special welcome to all new subscribers and welcome back to everyone else. I'm happy you made it here and thank you for your support of my channel. Let's get started with the feature comparison of the basic and the Plus versions of the SilverHat booster. From a track output point of view, the Plus version is identical to the basic version, up to 6 output channels with up to 8.5 amps DCC current per channel, assuming your power supply can provide this amount of power. Up to 4 of the output channels can be configured as auto-reversing channels, meaning they can be used to power reversing loops or track triangles without any additional hardware. All channels have individual short circuit and overload protection, and the overload protection allows for a temporary overload of up to 20% for a limited amount of time, depending on the fuse settings. The Plus version on top of this has either a DCC or a Loconet connection, and therefore can be controlled using DCC turnout or signal commands, and in the case of a Loconet connection, even report a short circuit or overload condition to Loconet, as we will see in a minute. Like in the last video about the basic version, let's first have a look at the boards needed to build the Plus version booster. We start with the same components. First, an Arduino board, either an Arduino Uno or Arduino Mega. Then a PowerShield for each output channel. The PowerShield generates the DCC current that goes to the track. And finally, a TinkerFace shield to connect the DCC or Loconet input. For the Plus version, we add a DCC AUX Shield between the top PowerShield and the TinkerFace shield. Adding an IoTT stick to the connector on the AUX Shield provides the upgrade to the Plus version with all the additional functionalities. As discussed in video number 143, these components are very similar to those you would need to build a DCC-X command station. And since I had this question asked from some users, I added a sequence in the last video that explains the difference between a booster and a command station. So, if you are not sure about the difference, please watch the explanation given in video number 143. Now, what is the reason for adding an IoTT stick to the booster? Well, the IoTT stick allows for supporting the additional functionality, as it can connect either to the DCC input or provide a full bidirectional Loconet connection. The DCC input can be used with any DCC system, and it can receive DCC turnout and signal commands to control the track output, the polarity of the reversing track, and to remotely reset the booster if needed. When connected to a Loconet system, these remote functions are available as well. But in addition to that, the booster can also transmit short circuit and overload information to other Loconet devices, so that it becomes possible to do a centralized control panel indicating the status of several boosters in one single location. With that in mind, let's build a Plus booster for 2 power districts and have a look at the additional configuration options. The first board is the Arduino, either Uno or Mega. It needs to be loaded with the SilverHat software which is quite easy to do, and it is the same software for both the basic and the plus version of the booster, as the functionality is the same. You can download the SilverHat software from the GitHub link listed in the description. If you want, you can download the source code and compile it for yourself, or you can download just the executable hex file, either for the Uno or the Mega. If you choose the source code option, you load the sketch into the Arduino IDE, compile it for your board type and upload it to the Arduino. If you do not have experience with the Arduino compiler, you can download the executable hex file for your Arduino type and the xLoader software. The download links are in the description as well. You unzip the xLoader file and start the xLoader program. Connect the Arduino to a USB port, select the SilverHat hex file and the Arduino board type. Then select the serial port the Arduino is connected to and click on Upload. It takes a few seconds and the Arduino board is programmed with the SilverHat firmware. Before we install the PowerShield board, it needs to be configured for the correct I/O pins. Also, this step is identical for both the basic and the plus version of the booster, so if you are already familiar with the process, you may skip to the next section. The DCC signal is coming in via I/O pins 2 and 3, so we need to set a wire bridge from pin 2 to PWM1 and from pin 3 to PWM2. If you are using an Arduino board with a USB Type B connector, make sure that the configuration wires do not stick out on the bottom side of the PowerShield, so that they do not touch the body of the USB connector, which carries ground potential. It is also a good idea to place a piece of electrical tape on the connector for some extra protection. I recently found some Arduino boards featuring a USB-C connector, which of course eliminates the risk. Next, we set the signal selector jumper to the PWM2 position. This means that the output will be driven from the two DCC input signals on pins 2 and 3. Finally, we have to set the wire bridges for the current sensor on the analog input field and for the power enable pin. If you want to use the auto reversing feature, you also have to configure the AR pin. If not, there is no reason to configure it. Here is a table with the recommended pin numbers for the maximum of 6 PowerShields that can be supported by one single Arduino board. Basically, you can choose any pin you want except for pins 0 and 1, which are used for serial communication, and pins 2 and 3, which are used for the DCC signal. In the last video I mentioned that you should not use pins 6 and 8 if you plan to use Loconet. That was actually a mistake. It is no problem to use them, as the connection of the Loconet signal to the stick does not use any of the Arduino pins. So, as shown in the table, that leaves you with I/O pins 4 through 13 to be used as power or auto reversing pins, and of course the 6 analog pins for current sensing. Following the table, you can build the booster with a maximum of 6 boards, 4 of them in auto reverse mode. Once the PowerShield is configured, it is placed on the Arduino board. Make sure all pins are inserted properly and there is no contact between the USB connector housing and any configuration pin. If you want to use additional PowerShield boards, configure them the same way and simply stack them up. Next, we place the DCC AUX Shield on top of the PowerShield. The function of the DCC AUX Shield is to provide 5V DC to the IoTT stick and the Arduino board as well. The IoTT stick can draw up to 200 mA when charging the battery, and this current may be too much for the Arduino onboard LDO to supply. The AUX Shield using the barrel jack can handle input voltages of up to 18 volts, without causing any problem for the Arduino board. It is even possible to use the PowerShield power supply for the entire booster stack, as long as your track voltage is not higher than 18 volts. To do so, bridge the V-in contacts on one of the power shields, which will power the V-in rail of the Arduino stack. The DCC AUX Shield is then supplied from V-in and generates the 5-volt supply for the Arduino stack. If you'd like to better understand how the DCC AUX Shield works, watch video number 130. Next, we place the TinkerFace shield on top of the stack. Make sure it is configured for DCC input, so the jumpers for pins 2 and 3 need to be set. The jumpers for pins 6 and 8 remain open. The other configuration jumpers should be set as follows. The interface voltage jumper should be set to 3.3 volts, as this is the I/O pin voltage of the IoTT stick. The V-in pin remains open if you have a Loconet command station in the network. You can close the pin to make the TinkerFace shield to act as Loconet master if desired. Finally, set the interface selector pin to either LN for Loconet or DCC, depending on the type of interface you plan to use. DCC for receiving commands via DCC signal, LN to enable bidirectional communication between the booster and the command station and other Loconet devices. Finally, we install the IoTT stick on the DCC AUX Shield and connect the Grove port cable between the IoTT stick and the Grove port connector of the TinkerFace shield. You can run a 10 cm Grove port cable through the hole in the AUX shield and connect it to the stick from underneath. That way it fits into the IoTT Cube frames, and all you need to do is breaking out the opening in the top PowerShield frame to run it through. Note that when using the IoTT stick, the serial communication of the Arduino board is used for the communication between Arduino and IoTT stick. Therefore, the USB connection from a PC to the Arduino board will usually not work. In case you wonder about the enclosure frames you see in this video, these are the IoTT Cube frames introduced in video number 108. These frames work for both an Arduino-based command station or an Arduino-based booster, and the 3D files are available on Tinkercad for download. The link is in the description below. I planned to talk more about the IoTT Cube frames in this video, but to keep it simple, I decided to make a separate video with more tips and tricks how to download and print them. So if you don't want to miss this and any other future videos, it is a good idea to subscribe to the IoTT channel and activate the notification function so that you are in a premium seat when new videos are released. Now, with the hardware built, the booster is almost ready. All we need to do is configuring the software for the selected I/O pins, which works the same way as for the basic version, except that with the IoTT stick it is done over Wi-Fi. The SilverHat is supported starting with IoTT Stick software version 168, which I released this week, and you can download and install it from the GitHub page as always. Once installed, you select the command source you want to work with. For DCC, it can be the DCC interface or DCC over MQTT. For Loconet, you can use the Loconet interface or Loconet LB server client or Loconet over MQTT. Yes, that is correct. You do not necessarily need to have a physical Loconet connection. Connecting via Wi-Fi does the trick as well. As hat module, you of course select the SilverHat from the drop-down list, and as usual, click Save and Restart to make the changes permanent. After rebooting, the stick web page shows the SilverHat tab. The LED chain tab is available as well, as it is possible to drive a WS2812 LED chain from the soldering pins of the DCC AUX Shield, with the onboard LED being LED 0. After the first startup, the pin numbers will be assigned as shown in the table, and the number of booster modules is set to 1. Use the drop-down selector in the Hardware tab to change the number of modules based on the number of PowerShields you have added to the stack. The sensor rate is set to 12.2 as needed for the PowerShield revision 5 and higher. If you are using an older revision 4 PowerShield, set this value to 8.31. The Loconet address is set to 1234 by default, and unless you want to use the Loconet feature and connect several boosters to the same network, there is no need to change it. If you use several boosters connected to the same Loconet, it is best to assign them individual numbers. Verify that all hardware settings are correct and make changes as necessary. Note that changes are effective immediately, but to make them surviving a reboot of the SilverHat, you need to click the Save to EEPROM button. Finally, connect the DCC track output of your command station to the DCC input of the TinkerFace shield. Or if your layout uses Loconet, you can also connect a Loconet cable into one of the Loconet sockets. Make sure your Loconet cable carries the track signal on pins 1 and 6, which is normally the case if it is connected to another booster, a command station, or another socket of the Loconet B type. If the DCC signal is received properly, the input signal string on the configurator will change from no input to DCC, indicating that a valid DCC signal is received. Now it is time to connect your power supply and perform a short circuit test. Again, other than using the stick web page, these steps are identical with what I showed for the basic booster, so feel free to skip ahead if you are familiar with the process. Make sure the selected power supply can deliver enough current for your layout. Ideally, the nominal output of your power supply should be about 20% higher than the booster current you are planning to configure. So if you want to have a 5 amp booster, your power supply for the channel should be able to deliver about 6 amps. It is also possible to connect a single power supply to more than one PowerShield, but the same rule applies for the sum of the currents. So if you plan to have 2 PowerShields set to 5 amps each, your power supply should be rated 12 amps or higher. Also watch videos number 138 and 141 for more information about choosing the right power supply. After connecting the power supplies, it is a good idea to perform a short circuit test. In order to have a safe setup, it is important to make sure the power supply can deliver enough current to reliably detect a short circuit and shut down the track power. To perform the test, click the Measure button in the Short Circuit Test column. The booster will shut down the track output so that it is safe to connect the 2 rails to create a short circuit connection. A new confirmation dialog window appears on screen, and when you are ready, you click the OK button to perform the test. The booster will switch on the track power for a few milliseconds and measure the short circuit current during that time. The value is then displayed on screen and helps you to determine the maximum current you should set for this booster. When you are done with testing all booster modules, click Save to EEPROM so that the values are properly stored in the booster. Now you can use the Options tab to set more configuration values for each booster channel you have installed. First, you can select the track status after powering up the booster. Note that this value impacts all installed modules. Set it to On or Off. Next, you set the nominal current for each installed booster module. This is the current that the module will be able to deliver on a continuous basis without going into overload mode. If you measured the short circuit current, the configuration page will show a recommended value based on the short circuit current your power supply was able to deliver during the test. To ensure the protection functions of the booster are working properly, you should not exceed this value for your nominal current settings. If you want your booster module to work in auto-reverse mode, click the checkbox. Then select the reset mode for each booster module. If set to manual reset, the booster will shut down in case of a short circuit, and you will have to manually reset it to restore track power. In limited auto reset mode, it will try to restore track power for a few times and then, if the short circuit remains, permanently shut down and wait for you to reset it. And in automatic reset mode, it will keep trying until the short circuit is removed and track power can be restored. The fuse mode drop-down box lets you determine how fast the booster reacts if a short circuit occurs, and also how long it will tolerate a current flow that is higher than the nominal track current you have set. You can try to set a predetermined characteristic from very slow to very fast, or you can experiment with your own value settings if you prefer. Higher values will make the booster react slower, and values should be multiples of 10. The next column has the actuator settings. It is displayed if your SilverHat is set to receive commands from either DCC or Loconet, and the Use Command Communication checkbox on the top of the page is clicked. For each booster module, you can specify commands for switching track power on and off, and for resetting the booster module via command input. If the module supports auto-reversing, you can specify 2 additional commands to set the polarity of the track output to forward or reverse. If the command source is set to DCC, you can control each output using switch or signal commands communicated over DCC. When using switch commands, you can activate the output by sending thrown or closed, and when using signal commands, you can specify any of the 31 available aspects of the signal command. In either case, if the command is seen coming in on the DCC line, the corresponding function is activated. If the command source is set to Loconet, in addition to switch and signal commands, you can also react to block detector and button inputs. Block detector inputs support free and occupied, while a button input can react on button down, button up, button click, and button double click messages. A common application using these inputs might be to use the turnout command of a reversing loop to set the track polarity according to the turnout position. That way, you do not rely on the short circuit pulse to set the polarity. The third column holds the reporting settings. It is displayed if the command source is set to Loconet. The booster can send out a message if a short circuit occurs or if an overload shutdown happens. As with actuators, it supports switch, signal, block detector, and button commands. Reports are basically a one-time message that is triggered when the event occurs, and they can be received by any other Loconet node. Therefore, it is possible, for example, to have an LED somewhere on a remote CTC panel that comes on if the booster detects a short circuit in its track district. Again, like with all other configuration settings, click the Save to EEPROM button to store them in the booster and make them permanent. Okay, that's it for the configuration. Now we can connect the track output, run the trains, and use the Monitor tab to see what's going on and control the booster as needed. On the Monitor page, the status of the input signal is displayed as well, so you can immediately see if the booster is receiving the DCC signal. If your command source is Loconet, an additional line is displayed that allows you to set the power status of the command station. Use the three buttons to set the power output to on, off or idle, as you are used to do when using a Loconet system. Note that these commands are sent directly to the command station, so if you send an off command, this will affect the command station output as well as the output of all connected boosters. It is the same command as if you would send a power command from a handheld throttle. The next two buttons allow you turning the track power of all booster modules on and off. These buttons are only affecting this particular booster and no command is sent to the command station. The actual track current consumption can be seen on the current gauge. The end of the green range indicates 80% of the nominal current, so if the nominal current is set to 3000 milliamps, the green range ends at 2400 milliamps. Yellow indicates that the booster is quite loaded, but still within the nominal range. Light red means the booster is operating above the nominal range and will shut down for current overload after a certain amount of time, depending on the fuse settings. Dark red indicates the current is too high and you risk to reach the short circuit trip current at the end of the dark red range, which will shut down the booster immediately. The load factor of the booster is indicated in the next column, as well as the output polarity of the reversing output if you are making use of this feature. In the last column you have the buttons to toggle the output power of just one specific booster module. A reset button to reset the booster after a short circuit if it is set to manual or limited auto reset, and a button to actively change the polarity of the auto-reversing output. Note that this button is only showing if the booster is configured for auto-reversing. So let's add a track load. As soon as a current is flowing, the gauge shows the value in milliamps. Also, track status and booster status is indicated. The load factor display shows to what degree the booster is loaded. If the nominal current is flowing, the load factor is 100%. If the current increases, the load factor increases as well, simulating a thermal model for the device. It allows you to go to a maximum load of 120%. If that threshold value is reached, the booster channel will shut down and allow for cooling off until a value of 60% is reached. Then it will restore track power automatically, independent of the reset mode, which only applies for short circuit shutdowns. And that's it for today. I hope this information was useful or at least interesting for you, and I gave you an overview how you can build, configure and operate the SilverHat Plus booster to meet the current requirements of your layout. If so, please use the comment section of this video to let me know your thoughts and click the like button below. That is an easy way to show your support for the IoTT channel and to promote this video to other model railroaders, because YouTube likes the likes. Thanks for watching and see you in the next video.